Great.
Of course, unfortunately, many of the students are now in the APMS, mental physical state meeting in Mexico. So that's why some of them will be joining soon. But I would like to introduce Professor Carlo R. He is a fellow physicist that is working now in the computer SIS, in the computer informatics system. Carlo got his bachelor in Brazil with his original from in the University of Rio Grande do Sul. Rio Grande do Sul, which is located in a region called Las Pampas. It is a beautiful region. Then he got his master's in West Virginia University and his PhD in Arizona State University. Then Carlo moved to McGill University in Canada, to Japan, to Shiba University, and then he went back to Brazil, to the University of Porto Alegre. So, and finally he joined the NAU this semester, and I think it's a really great opportunity to collaborate with him on interdisciplinary. So, Carlos, please welcome and welcome to
Thank you. It's a real pleasure to be here with you. So we're going to talk for the next hour about some electrical measurements using scanning gate microscopy. So first, we're going to start with coherent transport in nanostructures. Then I'll move to scanning gate microscopy, which is the main technique that I use to probe those properties of QPCs. Then some devices that we fabricated, some magnetic effects, mostly shouldn't cause the house in quantum Hall effect. Then
Could you speak a little bit louder so the people so close to the mic?
yes, closer to my portion.
So
No problem.
We had to do this last week because of the Zoom audio. So you have a choice.
Oh, that would work. Maybe close as much.
No, that's not good.
Yeah.
maybe it should be a volume.
Let's just turn it off. Yeah. Let's start all over. Better? Yes. Oh, excellent. Okay, so I was telling you that I'm going to start with quantum point context for unit transport. Then I'm going to talk a little bit about scanning microscopy, which is a technique that I use to probe those properties. Then I'll move to the Haas, quantum Hall effect, quantum chaos that we observe in these structures. And finally, some machine learning that I've been doing to try to understand better the properties of this device. So let's start with the question. Say you have a conductor, okay, and we are applying a current and measuring a voltage. So we know from Drude's law that the conductivity is given by n squared tau over m. But what if my device, the dimension of my device, is smaller than the mean free path of the material? Drude's law works perfectly for diffusive systems, but what if my device is so small that no scattering event happens inside it? How do we probe the conductivity of this guy? Well, we have to use quantum mechanics. So the first guy to study this kind of systems was Roughness in the 60s, 50s, more or less. And the idea is, if you have a dispersion curve, you're going to have more states towards one direction rather than the other. Then you do some quantum mechanics. We start with some simple equations, do some calculations, then use the one-dimensional DC of states, and finally you see that the conductance has a very specific value, 2e squared over h. That's the quantum conductance. Now, this was measured experimentally by this guy, Bart von Wies, from Netherlands in the 80s. So what he did was this. Here we have trenches, and the red thing is a two-dimensional material. Okay, so our electrons are forced to flow through this constriction. Since we have this constriction, we have quantized modes. As you can see here, this is the potential, and then you see the modes. Every time a mode passes through the Fermi energy, we get a quantum conductance. So we see this staircase shape here. Beautiful. It was measured experimentally, and we know this since the late 80s. Now, the technique of scanning the cosmos used to probe this kind of devices. This is my two-dimensional material, and it's shaped like a whole bar structure, so I can do electron measurements. And on top of this material, I use my scanning probe tip, and it is electrically charged. So I induce a potential in the two-dimensional material as I move the tip. And simultaneously, I measure changes in conductance of the material. So here's the tip. I move it on top of the device and measure simultaneously changes in conductance. Okay. So, if we consider that the induced potential is a delta function, and the perturbation is small enough that we can use perturbation theory at the first order, then doing some perturbation theory, quantum mechanics, we see that changes in conductance that we can measure are proportionally dependent on the local density of states. You see where I'm getting at? So I can do a map of the local density of states by resting the tip on top of the device while simultaneously measuring changes in conductance. So again, it's a big if. If the perturbation is very small, if the induced potential is a delta function, if the wave function is given only by states at the Fermi level, if the conductance doesn't change much, then the images correspond to the local density of state in the device. And again, it's a big if. So one of the pioneers using this technique was Bob Westervelt from Harvard, and he obtained these very nice images here. So this corresponds to the first plateau in the transmission curve of the QPC. So you can see one mode flowing. If you do the same at the second plateau, you see two modes flowing, and so on. You see three modes, and so on. This was very big. This was at the beginning of the 2000s. But this would correspond to the local density of states if those set of conditions were satisfied. Okay, so let's talk about some devices that I fabricated to probe those kind of ideas. So I started with this heterostructure grown by molecular beam epitaxy. This very simple machine here. So how does it work? So using molecular beam epitaxy, we can grow atomic layer by atomic layer of any material we want, with different compositions, doping concentrations, etc., etc. So starting with the indium phosphide substrate, this layer of indium aluminum arsenide was grown, then of indium gallium arsenide, and so on. So if you measure the bottom of the conductance band, what the structure as shown here, there's this small region that touches the Fermi energy, and this makes a two-dimensional electron gas. Where I have my two-dimensional system to work with. Then on top of this two-dimensional system, but then I do lithography and create a whole bar structure. So here are gold pads, where I can do electrical contacts. This is a mesostructure, so everything here is etched. So I have a two-dimensional system, and on top of this, I have this whole bar structure with electrical probes to be measured. Then on this whole bar, I created using etching quantum point contact. to probe this quantization of conductance. This structure is 2.7 by 2.7. So the constriction itself is something like 450 nanometers or so. The fees of the image. So when we put this device in a cryostat and lower the temperature to 280 millikelvin, instead of those beautiful plateaus that were observed by Bob Westerveld, we see this very strange curve with a lot of fluctuations. And using scanning probe microscopy, instead of seeing those modes flowing, we saw stuff like this. Something very strange. And the question was, what is it? It wasn't supposed to be there. Actually, the measurements were so nice that we got the cover of the 5 physics letters that year. Well, so we did some measurements to try to understand what was going on. Shubnikov the Haas, quantum hollow, quantum chaos. So the first one was Shubnikov the Haas. But to understand Shubnikov the Haas, we have to go back and do Landau levels. So what is it? So consider again, we have two-dimensional material and we apply a perpendicular magnetic field. So considering that we are in the coherent regime, we don't have any scattering event inside the material, it's all coherent. We take Schrödinger's equation, we put the magnetic field inside it, we do some simple calculations, and we see that the resulting equation is a harmonic oscillator-like equation. So we know the eigenvalues for the system, right? So they are equally spaced, and we have the density of states given by these peaks, which are called Landau level. Now, every time the Fermi energy passes through one of those peaks, we have a peak in conductance because we have some channel by the electron central. But we are on the peak of the peaks, we don't measure anything. And that's exactly what we have here. We have oscillations given by those Landau levels. Again, doing some simple calculations, measuring the spacing between the peaks, we can extract density of electrons in the two-dimensional material. So this is experimental measurements. So this is a real Shubnikov the Haas, the longitudinal resistance. And doing the calculations, we see we have a very high carrier concentration, but look at the mean free path, 1.2 microns at 280 millikelvin. So at 280 millikelvin, you would expect something like 15, 20 micrometers. But no, we have something very small, 1.2 micrometers. So what is causing this very small path? Has to be disorder. So basically we have a disordered material, and because of the disorder, then we have the very strange local density of states. Right. Now, quantum Hall effect. This granted Paul von Plitzing in the 80s the Nobel Prize in Physics. And it's very related, very similar to Shubnikov the Haas measurement. It goes like this. You take Schrödinger's equation, you do some manipulations, and then you see that current flowing along the y-axis is proportional to the electric field in the x direction, or vice versa, depending on how we measure. And what we see is that the conductance, when you divide the transconductance, when you divide one by the other, is proportional to E squared over H. Remember on the first slides, the quantum of conductance 2 E squared over H. In the quantum Hall regime, we have E squared over H. Similar. Actually, H over E squared is known today as the Plitzing constant. So let's see what can be done using scanning gate microscopy. Before that, okay, so here we have the Shubnikov the Haas oscillations and the quantum Hall effect. Every time you have a new edge state flowing through the device, you have two edge states, then you have one quantum of conductance. Similar to that first slide, but now using magnetic. So let's see what happens when we have steady gate microscopy in the device and a magnetic field. So the green dot is the tip potential, the induced tip potential. The black is the gate, and the gray stripes are the edge states caused by the magnetic field. The magnetic field pushes the electrons towards the sides, and then I have those edge states flowing. If the tip, the induced potential by the tip is close to the gate, it pushes the edge states, but it doesn't cause any change in conductance. So we say that this region is a compressible region of the quantum Hall regime. And this is here. So we don't see anything on the images. If we continue to move the tip towards the center of the QPC, eventually it's going to backscatter one of the edge states. And then you see a dip in conductance right here. So this is a region where you cannot do anything else. So it's called an incompressible region of the quantum Hall region. And that's exactly what we can see here using scanning gate microscopy. We see the regions of compressibility and incompressibility of the quantum Hall region. So we can visualize what's going on in the quantum Hall region, not only a measurement, some image. Now, quantum chaos, what is it? You know, chaos when you have two particles in a chaotic gate system, the orbits diverge, a little bit changing the small difference causes big changes in that divergence in the orbits and so on. But we are in the quantum regime, a little bit different. So we have this guy, Boreas, and he stated this: if your quantum system, its classical counterpart, shows chaotic behavior, then the quantum system is going to have fluctuations that are predicted by Gaussian ensembles. Was it clear? More or less. If a classical system has chaos, if you take the quantum system, it's going to have fluctuations that are dictated by a Gaussian ensemble. And there's something interesting about this because, for example, if you take a quantum billiard, we start to see those density of states that resemble classical orbits. These are called wave function scars. They resemble classical orbits. For example, here, a ball bouncing up and down, or more string shapes, and so on. But the key point here is that the fluctuations are given by Gaussian ensemble. So let's see what we can obtain using scanning gate microscopy. First, magnetoconductance curves. This is the magnetoconductance curves, magnetic field on the x-axis, conductance on the y-axis. If you remove this slowly background and take only the fluctuations, they are distributed according to a Gaussian unitary ensemble. Interesting. Now, if you take the images and take the fluctuations, exactly the same. The distribution of grains in this image follow a Gaussian unitary ensemble. And it doesn't matter what voltage we apply to the QPC, the conditions we measure the QPC, we always get this Gaussian unitary ensemble. So this is a big hint for us that electron motion in this disordered quantum point contact is actually chaotic. But as I said from the beginning, this is Mandelbrot. I love this saying by Mandelbrot. He says, clouds are not spheres, mountains are not cones. And I go on. Yes, delta G is not null. The TP potential is not a delta function. The states do not flow only on the Fermi level, and so on. So things are not this beautiful thing that we see in the book. Things are more complicated. But if what we are seeing is not the local density of states, what is it? What information can we extract from these images? The electron flow should be okay, because we are not arguing that we are monitoring the local density of states, but the electron flow. So we're blocking the electron paths, the see changes in conductance should be okay. The quantum Hall regime should also be okay because it doesn't depend much on the details of the potential, right? The edge states are pushed towards the edges of the center, would be okay. But what about the quantum tails, those more fine detailed structures in our images? Then it's problematic. So to try to understand what's going on, we started to do some theory. And to model the device, we use Green's functions. I will not enter into the details of the math, otherwise we'll put it quickly, or the general concept. So we use Green's functions, we use Dyson's equation to segment the image and do the calculation, massive calculations using massive GPUs, take months, it's extremely slow. But then eventually we can obtain the local, the theoretical density of states, given any specific potential. All right, so if we can produce theoretical density of states, given any potential, we can use something like a neural network to try to predict. So I feed the neural network with a potential and extract the density of states, or the other way around. I feed the network with the density of states and try to guess what the potential is. So that's actually very important because if I have quantum chaos, I want to know what potential I have. What does this disorder material looks like? And that's exactly what we did. Using Green's functions and cellular neural networks, we trained this network with thousands, tens of thousands of theoretical images, and then try to guess what the potential is. Literally, it takes months to train this neural network. Because you see here, the Green's functions depend on the inverse of a huge matrix. So we have to invert matrices over and over and over again. So it takes a long time. Well, so given a potential, we get the density of states or vice versa. We give the density of states and try to image the potential. So that's what we got. So this is the average potential in a disorder quantum point contact estimated by cellular neural networks. This is the variance, so changing parameters of my quantum constriction. I get variance and average position of these scatterers. This is a typical SGN image, and this is what my neural network produces. Something very disordered, not so trivial to understand. And from this, we can do a set of measurements to try to understand what's going on. For example, correlation, image correlation functions, cluster mass, and so on. But the problem here is that the images are very biased. So we fed the neural networks with some kind of potentials, and the neural networks cannot go over those training sets. So I'm feeding the neural networks with these disordered potentials, and all they can do is to interpolate and give me something similar to my training set. Can we do better? Certainly. So this one takes even longer. So if the previous one takes months, it takes at least 1 year. But the idea here is this: we use evolutionary search to try to guess the background potential. So how is it? We start with something like 100 different potential, random, completely random potential. There's no model. And then the one that produces a local density of states closer to the experimental one is the minimum. And it gives birth to several children. And then they compete again. And we do this over and over and over again until we have the biggest winner, which corresponds to an image 72% correlated to the experimental. And literally, it takes years using massive GPUs. So this is just a relaxation structure that we use. So it is over and over again, and then we can estimate the potential. And here it is. So I was not reading. Actually takes 1 year to do these calculations. So we just got these images by last month. We are still working, but we extracted something interesting already. So this is the experimental SGM signal, and this is the one produced by the evolutionary search. We can get back to 72% of correlation. If you let the algorithm run longer, maybe we would be able to obtain more higher correlation. But it's good, 70%, but it takes 1 year, so it makes sense. All right, so the image has some fluctuations. You can average out these fluctuations. If you do some averaging over the correlation length, no problem. So here's the raw image, and this is the corrected image. Ah, great. So now it looks like a disordered background potential. So we measured potential roughness. Now, of course, here it's going to be very rough because when we're close to pinching the QPC, any change in the position of the tip causes big changes in conductance. So yes, it has to explode. But this is interesting. As we go to higher conductances, higher transmissions, we see the formation of those very interesting patterns, which we do not understand very well yet. This is the potential distribution. We have the variance, we have the mean, so we can do a mean to variance plot. And you see that there's nothing special, it's just linear. So it's basically an homogeneous potential. If it was not, if there was some homogeneity, then we would see a power law or something more fancy. But it's just a linear plot, so my potential is homogeneous. No preferential. So we started to study the geometry of this weird potential. So here we have the cluster radius. You see here we have this very rough, very intricate potential. So it creates these little clusters. So you can study these clusters. Here we have, for example, the cluster radius, the average cluster radius, and a 2-point correlation function, which is the probability of 2 points separated by a distance or to be the second cluster. So we have here below 1G0, below 1 quantum of conductance, it starts to increase. Yes, because we are thinking QPC. But it goes in the other direction as well. So this means that as we are allowing more modes to pass through the QPC, we start to see some weird patterns be formed with the non-trivial geometry. So we did a calculation of the box dimension or the fractal dimension, try to understand the geometry of this potential. And what we see is that below 1G0, such as broad figures, which corresponds to the pinching of the QPC. So the tip is blocking completely the electron flow, and you see these big, huge, bold patterns. But as we increase the conductance above 1G0, we also see the formation of this interesting broad shapes, which again we are trying to understand. Finally, we have an idea of the alloy potential. We have a header structure, right? Drawn by ND. So we have an alloy, and we can image the average alloy potential. So it's very simple. We take all the images, we take the average and divide by standard deviation. So all those static features are promoted in the image. And here it is. And what is interesting so far is that they all match well with the standing gauge across of images. So it seems like, well, the SGMs do not reflect exactly the local density of states, but somewhat they are related because they match very well with the background potential. We see here dips always happens in low levels of the disordered potential. But again, we are still trying to understand this. So in conclusion, we talked a little bit about QPC, scanning gate microscopy. We saw that we have disorder in QPC and it's manufactured, especially when you look very low because of the need. Using scanning gate microscopy, we were able to see regions of compressibility in the quantum Hall regime. We also observed chaos. There's quantum chaos in this disordered structure. And finally, we are still trying to use machine learning to try to understand the background potential and what's going on. Thank you.
Thank you, Carlo. Some questions? Yeah. Go ahead.
Can you describe some of the reasons why you might want to design a device that is smaller than the proven design, or what would you
This would be fine. You see here, imagine that you tune your quantum point contact to this region, and then one electron goes out of your quantum computer device. It causes a big change in conduct. So you can monitor it. So this is a readout for a computing system. That's one of them.
Julie?
are you able to get what you understand? Okay, your machine learning model for
Several notebooks have a model, but the other one does not. The other one is model free.
is there any way you get any information? You get any information out of that about what is it, or is it
It's
just
going to get there. Very sure.
yeah?
Yes. So we're trying to understand the background potential, how it's related to the energy growth, economic. We're getting that. These are not full.
Please.
What? The GPUs are.
GPU.
RTX 90, Tesla, yeah, huge.
Which level device?
It's and it requires a 1,000 kilowatts power supply to it's monstrous. I don't remember the exact model.
Any other question? Can I have a question? It throws me a little bit the term of quantum chaos, because the way I understand chaos is that in the classical physics, you have a system with many bodies, many interactions, classical interactions, and then it's just a result of these many body interactions. So in the case of the quantum system, how do you correlate? Because you have the Schrödinger principle that we limit the amount of movement of, I don't know, I have always, not just in this talk, I always have very difficult ways to understand quantum chaos.
I don't understand it much myself. What is generating chaos in this situation is the potential, which is not. Basically, yeah, we need no linearities to have chaos. Yeah. So if it was a square box, you would not expect to have any chaos. But since we have this intricate disorder potential, it is non-linear, then it creates some chaotic motions in the quantum level. But the way we use to measure it is through the distribution of the fluctuation. That's how we can.
And then your material is really bidimensional, because you don't see any direct cones or anything.
No, it's not physically two-dimensional, it's electrically.
Electrical cone.
Two-dimensional
Not like
electron,
that.
yes.
Not like that.
It's three-dimensional. And there's something that I didn't tell you. That is it. If you take the Shubnikov-Lehaz measurements here, you see two subbands. So we have the quantum well here, and we have two modes propagating through the quantum well.
Okay.
So it is electrically two-dimensional with two modes propagating. Perfect, the two-dimensional.
And the last question, your instrument is basically atomic force microscope, or is that you modify it? Or is it special?
Yes, it was modified. It's a scanning probe microscope. Where is the?
No, the second slide.
Yes, here it is. So you have two piezo systems.
Huh?
So this is for non-contact, so it only vibrates in Z direction, and this one does the scanning. And this block is the tip holder. So we have to modify the tip because usually you put light and then you have optical detector with quadrants, and then, but we cannot afford to have light in our electrical system because it generates heat. So we have to modify it. So we have to use a piezoelectric tip, which we could only find in Japan. Yes. So we have to modify the electronics of the system to accommodate this electrical piezoelectric tip.
Any other question? Yes, please.
So the neural network, can you show the images that I generate for the neural network?
This one.
So and then you put it in neural network. Why you do this? You solve the equation, or you use the images, yes, and then goes to the law.
Equations, so it's a dynamical system. The silver neural networks are dynamical system.
So is there any way you can do an approximation?
All that I can tell us.
No, not that. I did it for a long time, but yeah, so I just wondering if there's any way to give you something that looks, you know.
We can, for example, this is a dynamical system, right? So we make it iterate over and over again until the errors below a certain level. We can increase the tolerable error, but then the images get undermined. And if we use a model free, this is already 72%. It's what we have.
Like, is the correlation linear or is it going to be exponential? Maybe not. Linear.
Julie, another question?
Have you talked to Michael about this little new?
Right, it does high performance computing.
Yes.
Yes, I have to talk.
He would be good.
Yeah.
Of course, the molecular beam epitaxy you show is the one you got for your startup package here. Okay, very good.
It's very simple equipment.
It's really simple for Pueblo. I've seen monsters. It's a tabletop model.
Yeah.
Very good. Oh, Brian, the last question. Oh, you asked.
Oh, I was just following up on, mentioned this linear, is that like? I think specify what I meant on the question is like the time that it takes to get your image correlated to what you actually have experimentally. With it's linear, that makes you got about 6 months left and you can get 100% correlation. But
Yeah.
what is the time that it takes? Okay.
Okay, well, we thank you very much. So he's local, so you can talk to him anytime.